the distributed shared memory and directory-based protocols. So this can be taken from Hennessy-Patterson chapter 5 to discuss the shared memory. It's also called non-uniform memory access. And there's also a primer on memory consistency and cache coherence here, but I think it's very well explained in this particular reference, and I've used it mostly in this particular lecture. So firstly, let us see what are the disadvantages of Snoop-based protocols. Now, in case of a snooping protocol, whether it is MSI, MESI, or MOESI, the problem is that you have to communicate over the bus with all the caches on every cache miss or on every write. So to indicate on every write, to invalidate the other cache blocks, and therefore the bus has to, the bus becomes a bottleneck in this case. Especially if you have more than 8 cores, then communication over the bus typically results in very heavy bandwidth over the bus, and it becomes a bottleneck. And therefore, beyond 8 cores, even if we were to put 100 cores with a snooping protocol, there would not be too much benefit with a multi-core kind of a system. So you would not see benefit or improvement in performance with 100 cores if you were to use a Snoop-based protocol, because the bus bandwidth is really is the bottleneck. So therefore, the solution here is to use a non-broadcast kind of network. So do not broadcast on the bus every time. Or in other words, we want to have a distributed memory and eliminate the need for broadcasting on every miss or on every write. So we've seen this diagram before. This is nothing but the distributed memory system, wherein for more than 8 cores, so here it's showing 8 cores, but assume that there are more than 8 cores. So you have the memory which is distributed across each of these cores. Now the idea behind the solution here, the solution is to have a non-broadcast network, and one of the non-broadcast kind of protocols is called the directory-based protocol. So here first we'll look at what is a single directory protocol. So typically what the processors in modern days do is they keep a directory with, or it is in other words like a table, which stores the state of each cache block and where it is present. And also the states are very similar to what we have seen before. It could be MESI, it could be MOESI. States are the same, and the way the states transition is also the same, but just that instead of keeping these states in every cache block, in every core, we're going to keep that in a table. And this table is typically maintained in the last level shared cache. So Intel i7, for example, maintains it in an L3 cache, which is inclusive. So this directory keeps track of the state of each of these blocks in each of these caches. So this is what is called a single directory protocol. So you maintain a single directory in the last level cache. But also Intel i7 improves upon this directory protocol by combining the directory and the snoop. So it gives the option of optionally snooping over the bus if it is free. And if the bus becomes a bottleneck, then it uses the directory structure. So it combines both of these. So how it works is the L3 is going to have this directory, and each core is going to have a cache controller, which is going to do a lookup in this directory. And then it is going to send the information back to each of these cores. So for example, if I have to do a read here, so earlier what we were doing is we were broadcasting a signal over the bus, and each controller would check its own cache and respond. So in this case, instead of that, you send it to the directory, and the directory will do a lookup, and it is going to now respond to this core saying either the data is present in the other caches or the data is not present in the other caches. Now, typically, the single directory structure is also a bottleneck because there's a single directory which does all the lookup. So mostly all modern processors use what is called the distributed directory lookup. So what happens here is that every processor has the directory, and this directory is not the same as the directory in the other cores. So typically the way it is done is, if there is a physical address of the memory, it is going to be split up into multiple slices, and it is distributed across these different directories. So for example, uh, address locations or blocks 0 to, let's say, 1000 are in one slice number 1, and they're going to be allocated to directory 1. Slice 1001 to 2000 allocated to the second core, and so on. So and they're also very well identified by the addresses. So for example, some bits of the address can tell which node it is present. So if this is called node 1 and this is node 2, some part of the address can tell you in which node is the directory present, and so on. So let us not get into the details of how exactly it's implemented, but let us discuss it at a high level. So the directory is actually distributed across the multiple nodes, and the cache coherence protocol exactly knows where to find the directory. So for example, if the cache block A is present in this directory, and this core requests for cache block A, then the coherence protocol knows that it has to look up in this directory. Otherwise, there's really no point in having a protocol, because it'll have to search in all the 8 directories. And if there are 100 cores, then it'll have to search in 100 directories. So it doesn't work that way. So typically, if you request for cache block A, then there is a very well used mapping or an address mapping, which tells you exactly where to look for that particular address. And what does this directory do? It keeps track of the caches that share that particular cache block. And it is going to also keep track of the states of that. So I'll explain that in more detail with an example. So now the cache states, they're the same. I'm not going to explain. So this is what Hennessy and Patterson describe, but you can just assume that it is similar to any other protocol that we have discussed. So shared state means that it is present in more than one nodes, and the value in the memory is up to date, that is dirty bit is 0. It is uncached means it is invalid. It is modified means that it's only one node has that particular copy, and it has returned to that block, and the dirty bit is equal to 1. And you could similarly have an exclusive state or a known state. And the state transitions are similar to the snooping protocol, any of those that we have discussed. The only difference is that the requests now do not go on the bus. There are no bus transactions directly between the cores, but they go to the directory. Let us look at an example. Let us assume we have core 1 and core 2, and they have their own caches. And this is the directory entry for, let's say, a certain address, block A. Now this directory could be present anywhere. So it could, let us say, be present in the core 2's directory, let us assume, for example. Now let us say the core 1 requests for a read on block A. And let us say it is a read miss. So it is currently in the invalid state, and it is requested for read of cache block A or address block A, and it is a read miss. Now this read request is going to go to this directory, which is present under core 2. So which means if you go back to this structure, we have requested from node read on the node 1, and that particular block A is actually present as part of the directory here in node 2, and the request has gone to that particular directory. Now it is going to have a certain format here. The first one is that it's either going to say that the particular cache block is dirty or not dirty, and it's also going to have a certain number of presence bits. Let's say this was an 8-core processor. It's going to have 8 bits here, indicating where is that particular block present. Now all zeros indicate that currently this data, which the core 1 requested on the block A, is not present in any of the other cores, which means that it has to be actually read from the memory. So all of these 0 bits indicate it's not present in any core. So the data is now going to get fetched from the memory. So the directory is going to now send a response to the memory controller to fetch the data from the memory, and it is going to send that to cache 1. So it's going to send the data to cache 1. The directory sends the data to cache 1. And similarly, if we're doing a messy protocol, it's going to change that state from I to E state. And and it's also going to update its directory. So it is going to now say that this cache block is present in core 1. And it's also going to change the dirty to 1. That is because next time when this is going to have an exclusive access. So if it in future writes to the data in this particular block, let's say core 1 now has an issued a write, then this can easily change from E to M without having to indicate to the other cores, because E to M can change without any transaction. Therefore, we go to have this dirty bit equals 1. Now, what is the advantage of having this directory-based protocol? So the advantage is that, let us, for example, assume that there is another core, core 3 or core 2, which is requesting for another block B. Now, this is going to have to look up in another directory. So this is just one row of the directory, so it can have multiple rows. So if at the same time when core 1 issues a read for A, core 2 can also issue a read for another block B, and parallelly this lookup can happen in another directory. And this directory could be present anywhere. This directory could be present in the same core 2, in the same node, or in a different node. But the point is that you could independently and parallelly do the directory lookup, and without having the bus as a bottleneck. So that is the key advantage of the directory-based lookup. So let us take another example. So now let us say we are in this particular state, and now core 2 is now trying to write to the same block. So again, this request goes to the directory, not on the bus. And the directory says that this block is actually currently in core 1 already. So the directory forwards this request to core 1, asking it to invalidate its data because core 2 wants to write to it. And similarly, as earlier, this I would change to M because it's trying to write to it. And the directory has sent this invalidate on the bus to core 1. And once this core 1 actually invalidates the data, it has to send an acknowledge back to the directory saying that yes, it has invalidated it. And once the acknowledgement is received by the directory, it is going to change its state, the present state. So it's going to remove it and make it 0. So earlier this was 1, and this is now changed to 0. And then core 2 is now going to write to it. So we're going to update the presence bit in core 2 to 1. And similarly, we're going to keep the dirty bit as 1. So that is the key advantage of a directory protocol. You avoid the bus transactions as much as possible, and then you involve the directory as much as possible. Now, Hennessy-Patterson also described a few more terminologies. Let me explain that here. So let us say we have four cores or 4 nodes. The node on which the request originated is called the local node. So if the processor 1 requests for a read on a certain block, that is called the local node. However, the directory information for that particular block A may not be present in that local node. It is present probably in core 3. That is because of the way in which the memory address has been split up and sliced into the different nodes, and therefore it is present in core 3. So it has to look up in the directory present in core 3. And this node is called the home node. So of course, this could have been present here as well, in which case the local node will be the same as the home node. Now the physical addresses, like I said, is distributed so that the node contains the memory and the directory information. It also contains the cache state information. And a particular node always knows where is its particular directory present. So it doesn't have to look up in every core. I mentioned earlier, you can actually have an address structure such that if once you issue a request for cache A, you know where is its directory present. So it is present in 3, therefore you directly go to 3. Now, when we request for the data, now this data can be present in some other core. Let us say this data is present in core 4 already. So such a core is called a remote node. So a remote node is a node which has a copy of the cache block already. So this is the terminology: local node, which requests for the data; home node, where the directory is present; remote node, where the cache block is present. Now this table is also from Hennessy and Patterson. They describe the directory protocol in a different manner. So I'll just describe a few of these. So here P means the requesting node and A means the requested address. So let us say, for example, we have a read miss from a particular core. Then the originator is the local cache and the destination is the home directory. So you're going to look up in the home directory. So node P, that is the requesting node, has a read miss at address A. It requests the data to the protocol. It requests the data to the directory. And the directory is going to provide either the data from another core, in which case it will make it a sharer, or it is going to get it from the memory. So similarly, on that same thing happens on a write miss. But on a write miss, the P, or the requesting node, will become the exclusive owner. Now, when you have to invalidate a certain block, the invalidation request goes through the directory to all the other remote caches that have the cache blocks. Now, if the invalidation originates from the directory, it invalidates all the shared copies of the data in all the other cache blocks. Now, if there is a fetch request from a home directory to a remote cache which has the data, what the directory does is it fetches the block and sends it and gets it to the home directory, and then it sends it to the requesting node, and it changes the state of the address in the remote cache. Then similarly, if you have to fetch or invalidate, again the request originates from the home directory to the remote cache to invalidate the blocks if needed. When the data is returning, and if the home directory has requested for the data is going to return from, let's say, either the memory, the local memory, because the memory is again distributed, and the destination is the cache. And whenever you want to write back the data, let's say the originator was the cache, the destination is it is going to send the data to the home directory, and the home directory in turn is going to send the data back. So overall, the point to keep in mind is that there is a directory structure which is going to be looked up. The directory can be present either in a shared L3 cache or in local nodes. Preferably they are in local nodes, individual nodes, and then the data is routed through the directory. So for a more comprehensive example, I would suggest you to go through this 4-core example at this particular link.